So we've made some progress in understanding astronomical phenomena and the way they change periodically. We've got the sun, we've got the moon. Let us close this discussion with some interesting relations between astronomy and timekeeping. I told you that units of time kept being defined in terms of the Earth's rotation and its orbit. This is not a coincidence. We want our time to match what's going on. We want 6 a.m. on our clock to be solar sunrise because that's the time we go out and plant things, work in our fields. And so our 24-hour days are adjusted to be the mean solar day. Our months, the 12 months into which we traditionally divide the year, are approximately lunar. The synodic lunar month is 29 and a half days. Our months are a bit longer than that, and this allows for the rare phenomenon of 2 full moons falling in the same month, which is what colloquially is called a blue moon. It's a rare phenomenon. It requires a full moon right at the beginning of the month, but it does happen. Our definition of a year is designed to match the orbit. A year is 365 days. The Earth orbits the Sun once every 365.2564 days, a little over a quarter of a day. This is a sidereal orbit. In other words, this is the time that it takes the Earth to return to the same position in the sky relative to the Sun, or the time it takes the Sun to return to the same position in our sky relative to the stars, hence a sidereal orbit. The first thing we observe is that the year is not, unfortunately, an integral number of days. This is a problem. It means that since our days turn over every 24 hours, that every 4 years, your timekeeping, if you have a 365-day year, then every 4 years you are off by a day relative to the Earth's orbit. So who cares? Well, accumulate those days for 180 intervals of 4 years, and now you are off by 180 days, which is half a year, which means that now January corresponds to northern summer. This is very inconvenient if you're trying to plan agriculture. And we have a solution to this, right? This was discovered by Julius Caesar, or in his time, and it was his legislation that added leap years. Once every 4 years, we add another day, making that year 366 days long. The average year is now 365 and a quarter days long, and now we never drift more than a day off from having our orbit match our calendar. However, this is not completely precise enough. In fact, what we want our calendar to match is the seasons. The seasons have to do with the relation between the Earth's position relative to the Sun, and not the stars, but the direction of the tilt of the celestial North Pole, or the terrestrial North Pole. And remember that wobbles to the west rather than to the east. So a complete rotation where between solstice and solstice, or equinox and equinox, is a little bit shorter than the sidereal year rather than longer. This is called the tropical orbit. The mean time between solstice and solstice is 365.2422 days. Remember that the precession is very slow, takes 26,000 years, so it's not a big effect over a year, but it does make the mean tropical year a bit shorter than 365 and a quarter days. This was understood in the 16th century and led to the correction from the Julian to the Gregorian calendar. Correcting for the deviation between 0.2422 and 0.25 required removing some of the leap years. That is why on centuries that are not millennia, in other words, years whose number divides 100 but not 1,000, we do not add a leap year. We do not add a 29th day of February. Those years are only 365 days long. The average year is a little bit less than 365 and a quarter days long. In fact, it's close enough to this number on average that it'll be millennia before we have to make another correction. And so we definitely use astronomical phenomena to adjust our clocks and our calendars, not for any silly reason, but because astronomical phenomena govern our life, and we need our timekeeping to match that. It's quite an elaborate universe we're starting to build around us. We have the celestial sphere where the stars are fixed. We have a solar sphere that rotates relative to the celestial sphere about this tilted axis so that the sun can move along the ecliptic. We have a lunar sphere tilted relative to the ecliptic around which the moon moves a little bit faster. Moreover, all these tilted trajectories are also wobbling to the west, one very slowly every 26,000 years. The moon's a little bit faster every 18.6 years. This is very elaborate, but it does explain everything we see, the alternations of day and night, the phases of the moon, eclipses, seasons, almost everything. Let's go to Athens and see what we might have been missing. We're back to our favorite picture of the sky in Athens. And I've allowed the software to show us the ecliptic. And we see the 23.5 degree tilt relative to the celestial equator. We see the intersection of the ecliptic and the equator here at the prime meridian in Pisces. We still live in the age of Pisces. And we see that the part of the ecliptic that's visible at night is mostly the part north of the equator. That's reasonable because end of November, the sun is well south of the equator. The part of the ecliptic that lies south of the equator is what we see during the day. So far, so good. The other thing you'll notice, and I'm sure if you tried to run your own simulation, and certainly if you went outdoors, you will have realized by now that I fudged. I suppressed some things in the simulations I've been showing. In particular, the two brightest objects in the sky were omitted from my discussion up to now. One of these, the brightest of them, is this waning gibbous moon, which we see here. A waning gibbous moon, remember, is a moon that is past full, and so it rises after sunset, and at 9 p.m. we're still seeing it in the eastern sky, so we expected that. The moon happens to lie very close to the ecliptic right now. It could have deviated, remember, by as much as 5 degrees. We also have the next brightest object in the sky is the beautiful planet Jupiter. And we have not brought up planets. And once we allow that, we see that scattered along this ecliptic are a few others, non-star objects, Neptune, Uranus, and the asteroid Ceres. And if we look at this image over time, we would notice that, like the moon and the sun, the planets move as well, which means we're going to have to start next week by adding even more moving parts to our universe and enriching what we know and eventually leading us to much, much deeper understandings.